Okay, all settled. Here we go again. I finished yesterday with public announcement logic. Yeah, public announcement logic was the logic of knowledge, where you have an operator for knowledge change, which has as a parameter a formula of the language, and of which the execution meant that you restrict the model to all the states where the formula of the public announcement is true. So to refresh, well, that was to refresh our memory, but to enact this, I'm going to do a classic in the area, which is called, well, you might possibly tell what it's called. It's called the muddy children problem. So, this is the riddle. Okay, who doesn't know the muddy children puzzle? Okay. Who does know the muddy children puzzle? Okay. Who is in the third category? Okay. In logic of knowledge, this is not possible. Either you know it or you don't know it. But yeah, there's no third category, but that's fine. Real life is always more complex. So it's a bit smaller, but this is a very bright screen, right? So I think you can read it from the back, I hope. Yeah. Otherwise, come to the front, there is more space. So we have a group of children. They've been playing outside and are called back into the house. They get around the father, they have a father, and some of them have become dirty. In particular, they may have mud on their forehead. What's the idea with mud on your forehead? That you can see it on the head of other children, but not on your own head. Agreed? So this is some epistemic setting. Yeah? So you do not know if you are muddy, and you do not know if you are not muddy. Yeah? In terms of English, you do not know whether you are muddy. So the whether stands for not being able to determine the value of muddiness, whether it's true or false. Father now says at least one of you has mud on his or her forehead, and then will those who know whether they are muddy step forward? If nothing happens, then he repeats this question, well, until something happens, if something happens at all. So the question is, will something happen? An immediate question to you that I now have is, what does this have to do with public announcements? I could see at least one of you has mud on his or her forehead as a public announcement, but will those who know whether they're muddy step forward? That looks more like a question to me than a public announcement, right? So, well, what would be the announcement in the setting of this riddle? This is one of the things that we have to ask ourselves at first. Oh yeah, it's an imperative. It's not a question. Yeah, yeah. Okay, yeah. So there are many speech acts, and I should have known that one. So what's the public announcement there? If there is something going to happen at all that we can interpret like a public announcement? Well, I've been talking a bit on almost demotivating the word announcement, right? So this is a logic of publicly observed events. And in this case also, the publicly observed event that we're looking for is this stepping forward. So it's you might say the response to the imperative. Yeah. Okay, so this makes it clear again, like public announcements can be things said, public announcements can be things observed, like stepping forward. Public announcements can be the exhaust of an IMSC car, and in this case, public announcements can actually lead something not happening. This is actually rather weird, because to define a non-action is typically rather hard. So what we will see here is that you can have a non-action in the setting of a problem description where you have a protocol. And then something not happening is an action in terms of protocol. But let's first do the puzzle. We now can model this as an epistemic model. where you only do not know your own state, and the case for 3 muddy children, where we model a state of the world as a triple of 3 digits, 1 and 0, where 1 means muddy and 0 means not muddy, means that in this case, for example, B cannot distinguish the state wherein the second digit is 0, wherein he is clean, from the one wherein the second digit is 1, wherein he is muddy. And as for the cards, the perspective for different agents is different, and for A, it's the first digit that matters. Now, you might say this models the initial situation, and our father says at least one of you is muddy. This is a public announcement. We now know that public announcements restrict the model to states where the announcement is true, so that eliminates the state where it is false, which is the 000. So we get here. That was easy. Now the question is, what happens when father says, will those who know whether they are muddy, please step forward. Here I've actually been silent on one aspect of this setting for 3 children, although if you recall the way I depicted my models, you will have noticed this. One of these states is here underlined, so this is the actual state of the world here. In the logic of knowledge, you have a model, sort of establishing the situation, but an actual state of affairs in which you have to evaluate all the propositions. So here N and Bill are muddy, and A and B are muddy, and C is not muddy. Given that most of you seem to know this riddle, I can go through the explanations fairly quickly. If I'm being told that at least one child is muddy, and if I'm a child, and I see no other muddy children, I must be muddy child. There are 3 such situations in the picture where there is one muddy child, this. So here, somebody would now have stepped forward. If, given that this is the actual situation, nobody steps forward, we therefore know that these 3 corners of the cube can now be excluded. So the transition must be the one that removes these 3 corners. Well, so far so good, but we have now also learned about public announcement logic as, something wherein the public announcement is represented by a formula. So despite telling you this hopefully nice story so far, what is then that formula?
You mean the formula?
Yeah.
For the announcement?
Yeah.
So it must be something like that, MA or MB or MC, no?
Well, something like that, but it's a bit more than that. Yeah. So what more? Yeah. So this is indeed the point. So the announce. Well, you're supposed to step forward if you know whether you are muddy. So if you know that you are muddy, or if you know that you are not muddy. And we now have you might say, the elements to describe muddiness, which is this, and this. So the formula to describe that you know whether you're muddy, this is for one child, for example. I know that I'm muddy, or I know that I'm not muddy. And then you do this for all 3 children. And then you know that that is not the case, because nobody stepped forward. So that would be the formula. I'm talking my way through the next slide, and this is then the formula. So we were here. These are the states where there's one muddy child. And the formula that is exactly true in those, but not here, is this formula. Yeah?
After that, anyway.
Yeah. So, I was hesitating between, you have to choose an order in doing this. Yeah. Indeed. So, the result of announcing this formula is this model, and then the result of announcing this formula is this model. Yeah. So this model is the well, the transition from this one to this one. Yeah. We can also almost observe this visually. Here there is a C link, here there's an A link, but there's no B link anymore, right? So here B would have known that he's man. Here there's a B and an A link, but no C link, so here it will be for C, etc. Okay. Now, well, that was the riddle. There's a reason why I do this riddle in detail, because I do a variation later on that will be more relevant and that might be new for you. If we now repeat this request, now here we see that there's no uncertainty left for A and B. So now the formula, if we check this formula, will be true here. And by the way, if you see this as a protocol where you always have the, you might say, the non-deterministic choice between knowing whether you are Modi or knowing or not knowing that, that would split actually and not restrict the model into these three states and that one, wherein the agents still wouldn't know, or the children still wouldn't know whether they are Modi. Yeah, but that will be a more, well, this explanation in terms of protocols, on which one Yanjing Wang will talk tomorrow, will be a more, you might say, appealing, fuller explanation for this riddle. But in the setting of public announcement logic, where announcements means model restriction, you can't sell it that way. That's a bit funny. Yeah. So, Chuck, done. Yeah. Now, so actually what happens is now that A and B step forward. Yeah, sure.
The announcement, the formula, it is like, sorry, the previous slide.
Yeah, so here the small difference is this, right? Yeah, yeah. So given the state, so yeah, it's a good one. So given the state of your knowledge, in this particular model, this one survives given that this was the formula with, and here you, in the previous moment, you didn't know whether you were Modi. But the next state, where we end up here, it survives because you, well, A and B know that they are Modi, and therefore this disjunction is being satisfied because the first two disjuncts are true. Yeah. Yeah. And, yeah. Okay. Okay, enough for the Modi children. Just to mention a bit, there's a nice story on the origin of this riddle because it goes back to the early 19th century. I won't be talking about that in detail. Yeah, so there's a nice story about that, but you can read it up on the presentation later. Okay. Well, this was the exact spot where I stopped yesterday, and we actually had been talking our way through this axiom, right? In fact, you have such, well, this I would call a reduction axiom because it's an equivalence with something on the left side and something on the right-hand side. In fact, there are reduction principles for all of the logical operators that you can find on the right-hand side. So there's also a reduction for negation, which says phi implies not phi psi. This is also an equivalence. Axioms such as this reveal the partiality of the public announcement operator. Yeah? It's not merely a public announcement, but it's a truthful public announcement. So its execution as a program depends on the, well, on the truth of the announcement formula, but this is like a guard to execute the program, and therefore if you, well, looking at connectivity of logical operators, they commute, but depending on the guard being satisfied. So here you find the guard, which is the formula, so then it becomes implicative. It also distributes through conjunction. If we have something known after public announcement, that is again, well, that commutes, but subject again on the executability of the program. And there's also a trick for combining two announcements, because you may recall that I have presented the syntax of this public announcement logic as well, fully defined by a BNF syntax. So announcements themselves may also contain announcements. There's nothing against that. And therefore, in a way, this rule says that if I have one announcement and then another announcement, and I want then to check a condition chi, that's equivalent to, well, chi followed by a single announcement, and the single announcement says phi, and after announcing phi psi. It's like replacing, if you have a model transition, you transform it into another model, you have another model transition that transforms it into a second model, you replace the two arrows for the model transitions by a single arrow. And that single arrow says, no, that combines the effects of two announcements. Now, if you look at this, this schema, you can, and given that these look like what I said, rewrite rules, there is something funny to observe about this rewriting, namely that if you go from the right to the left, the announcement operator goes deeper into the formula. Now you can imagine executing this schema, repeatedly. You start with the public announcement operator, well, before the K operator, say, you push it beyond the K, and now it's before another formula psi. This psi may actually be something of this form that is a conjunction, and then you can push it through the conjunction, and then you have a chi here, which may be a negation, and then you push it through the negation, and at some stage, you push it deeper and deeper into a formula. At some stage, you will reach a propositional variable, and then there's no further pushing to do because you can get rid of the square brackets. So it's a way of eliminating public announcements from, well, formulas containing public announcements by rewriting it into equivalent formulas without these public announcements.
So for this, do we need the last axiom? Public announcement twice?
Yes. So there's a trick. So you have to define a complexity measure that is well-founded, and that states that this is of lower complexity than that, and that can indeed be done. But yeah.
We thought that can be done.
Yeah. But that's very relevant indeed. Without that, it doesn't work. Yeah. So all this is trivial. This is not trivial, indeed. Yeah. You can, it can be done. I could explain it, but I realize that I have now 1 hour left, so maybe I should not explain it in detail. But
my question was different. I was thinking, do we need that axiom? Because it appears to me that we thought even that axiom, public answer formula can be reduced to without involving.
oh, I see. That is correct. I see. Yeah, that's also a good point. That is correct on the condition that you follow an inside-out reduction strategy. But in order to be allowed to follow an inside-out reduction strategy, you need another principle that says that in formulas, you're allowed to replace a subformula by an equivalent other formula. If you have this principle as an axiom, you can derive that principle, the substitution of equivalence. If you do not have this principle, you need that principle of substitution of equivalence in order to obtain the same result. So there are a number of different versions of axiomatizations of public announcement logic, and one of the variations that you have is, well, to choose between substitution of equivalence or adding this as an axiom to the system. Or even other variations. So if you want to know about variations on public announcement logic, ask Yanjing Wang. He knows everything about public announcement logic variations. Yeah. Okay. So in a way, so this story, this part of the story is the story about eliminating public announcements from a formula by rewriting it into an equivalent formula. This has already been observed at the outset, you might say, by Plaza and also by Gebrandi, by the people active, having established this logic. There are some further interesting observations there, on which I will also not go in detail, but I want to mention them. One thing you can observe is that if you go, for example, to the right from here to here on the left-hand side you have one occurrence of phi, and here you have two occurrences. And here you have one, here there's two. So by doing this procedure repeatedly, you have an exponential blow-up. Therefore, it means that even if you find an equivalent formula in the well, in the standard epistemic logical language, it might be interesting to know how the length of this equivalent formula compares to the original formula you started out with. Well, this matters for some applications, but not for other applications. So if you're interested not in preserving truth, but in preserving satisfiability, there are other ways to do this that do not have exponential blow up, so it doesn't matter for the complexity of the logic very much. But for model checking, it matters, and there are results that say that this public announcement logic is really more succinct than the basic model logic in a technical sense, that you can construct two sequences of formulas such that, well, the one sequence is always of, at least exponentially shorter lengths than the left sequence. But that requires more proof than just this rewriting, because then you have to show that really no other formula at all exists that has, that shorter length. And not this particular formula that you happen to find by this rewriting. So that's an interesting story, and on this story there have actually been recent results. Well, I allow myself a smaller diversion, because the standard setting wherein these succinctness results are obtained work with trees, and trees have a direction, and the logic I presented here doesn't work with trees but with equivalence relations, and succinctness results are harder to obtain if you have equivalence relations. So there's some interesting stuff going on there. The other thing I wanted to mention is that here we have another thing in red, because I've also been talking about common knowledge. So if you have common knowledge, and you have a common knowledge followed by an announcement, well, then I don't have something of the convenient form that it's equivalent to something where the formula is pushed beyond. Well, then I have to do it indirectly in this way. I could give you the field, the interpretation for that, but I won't do that, but merely mention that here we have infer. So we have a derivation rule, and this in itself does not prove anything yet, but if you have the red thing, the logic is more expressive, and you can really do more things than merely this, because you can then not eliminate the public announcement operator. So if you add this common knowledge, then, well, you can do more things with the logic. Now, you may remember that I presented this relativized common knowledge, and the nice thing is that if you have this relativized common knowledge, then again you have a reduction principle that is an equivalence. So if instead of the standard common knowledge that we know, or that I presented yesterday, you present this by another modality, relative common knowledge, then again we can eliminate public announcement from the logic by rewriting it to an equivalent expression in the logic with knowledge and relativized common knowledge, and those logics are therefore then equally expressive. Of course, also here everything comes at a price. The logic with relativized common knowledge is already very expressive. So, yeah. Okay. That will be a story, but I want to give you the impression of other things too. You had a question, yeah, sure.
A good example of an announcement or observation of a common knowledge.
An example of a public announcement after which you obtain common knowledge of some kind or other?
No, the announcement itself is a common knowledge.
Well, if the announcement itself, yeah, well, this is it's a trick question. If the announcement is a common knowledge formula, well, the thing was already commonly known. Well, the condition for executing an announcement is truth of the announcement. So if it is already true that formula phi is common knowledge, then common knowledge announcements. Well, for example, in the muddy children problem, you could say it's common knowledge that everybody knows whether he's muddy, right? Well, no, if that were a truthful announcement, then that wouldn't change the situation. So common knowledge formulas have the property that they are true after the announcement. And if you recall this small thing about the unsuccessful updates and the successful, well, the unsuccessful update was saying P and not KP, and after that it's false, right? Because you know P. So P and not KP is no longer true. The formulas that remain true after being announced, such as propositional variables, you can give a name for that. You can call that successful formula. And well, we are not yet there because if you announce P, well, you have KP, but if you announce P, you actually have, if you have more than one agent, common knowledge of P. But common knowledge as a modality satisfies transitivity. So in fact, you have, after announcing common knowledge of common knowledge of common knowledge of phi. So a formula like P and a formula like common announcement of anything share the property actually that they remain always true after being announced. And those are called the successful formula. Yeah. That is one proviso. Yeah?
Muddy children case, you say there's common knowledge that at least one of us is muddy, then it's clearly true, this statement, because the thing reduces to an empty model. So maybe Jack is asking for things where you have a non-trivial result after the...
Okay.
I'm wondering whether it's only a formal device to have any formula in the announcements. You know, syntactically, you allow any formula in the announcements. Is it only a formal device or does it actually have some inference involved? I can understand the use of K formulas, but anything more.
Well, you could have things like well, just theoretically, you could say non-K Q and common knowledge P, for example. You could combine common knowledge with other things. Yeah, but no, an example with a common knowledge formula that has been publicly announced is trivial. Well, doesn't exist because they are all trivial. Yeah, that's the short answer. Yeah. Unless it is not common knowledge of the set of all agents, but common knowledge of a subgroup.
Yeah, that's it.
So if in a security protocol, after having exchanged their secrets, the sender and receiver announce, well, it's now common knowledge between us that we know the secret, that could be quite informative for an eavesdropper. But if in this setting for three agents, sender, receiver, eavesdropper, it's being announced that they all three have common knowledge that sender and receiver now have exchanged secrets, that's uninformative. Yeah. So you can do interesting things with common knowledge, as long, even with public announcements, as long as it's common knowledge for a strict subset of all agents. Yeah. Yeah. Okay. I'm definitely going to run out of time. Yeah. I won't. I'll just stop at some stage and then we're going to have coffee. Yeah. I can't see, what's the time now? It's 10 to 10?
Yeah.
Okay, okay. It's only halfway. Yeah, good.
The original model was not connected.
Yeah, no, yeah. Yes.
The muddy children problem is always stays connected. Maybe that's...
But if you have a connected part of the model, that's a bisimulation invariant, so then you are still fine. Yeah. So yeah, true. We have seen this. Having gone through all the trouble to talk you through public truthful announcements, it might still be nice to look at an alternative semantics for announcements that doesn't assume that announcements are truthful. Then you can just say anything. And this is interesting if you want to say anything. For example, if you want to lie, right? And you want to convince others of that what you say is actually true. So you could do some things related to that. Also, this comes at a price, but the price comes at the end. So let's start with the good part. You might say a disadvantage of public announcement logic, yeah, is that it's assumed that what you say is true. The recipe to execute a public announcement is that you reduce the model to the states where the formula is true. That's a consequence of that semantics. If your goal is, well, not if, but your goal of announcing is to affect the beliefs of the people you're addressing, right? That the people who incorporate this new information, these agents, change their beliefs. So you might as well take a semantics that affects the beliefs of these agents in the system only, and that's all you need, and then you're done. So an alternative semantics for public announcement is the one where you do not remove, well, where you might say you do not only keep the states in the model where the announcement is true, but you only keep the arrows, the pairs in the accessibility relation, pointing to states where the announcement is true. That's all. So instead of removing states where the announcement is false, you keep the entire domain of the model, you keep all states, but you just remove the arrows pointing to states where the information is false. If you do that, then, well, then you get this. And we could do this technically, but well, I hope that what I have explained to you is essentially that technique. Do not remove states, but remove arrows, remove pairs in the accessibility relation. And, well, and that sounds nice, because then at least the changed model is easier to define, because the valuation remains the same, the domain remains the same, you only change the accessibility relation. Now what is the price? Well, the price is that then the announcement, well, indeed, no longer depends on the truth of what you say. So that means that, well, that relation is lost. And if you look at this logic of announcements as something that, well, makes it possible to reduce uncertainty about something, and approach the truth, well, you only approach what people are willing to believe about the truth. But there's no further relation between the truth of formulas and what people will believe about these formulas. So you have this alternative semantics as at the price of everybody becoming extreme agnostics. Yeah. Okay. But you can then define lying in such a setting, because a lying announcement uses this semantics. But if you lie, you say something that you know to be false, and then lying in public announcement logic is lying by an external observer, an external entity, right? And an entity that is not modeled, such as, well, God. So lying is an announcement by the devil, and an announcement by the devil has a precondition for its execution that, well, anything the devil says is false. So then the condition is that the formula phi is false, and then you perform this arrow reduction operation, and you check the post condition. This is not a very smart devil, because once you figure out that it's the devil, you just reverse the truth of anything he says, right? So there are smarter ways too, but this is not modeled in public announcement logic. Yeah. Yeah. There are yet other semantics for public announcements, but I will not talk about that. Yeah. Okay. Yes.
Not the removing arrows model, the removing states model. If we announce, I mean, the model lying, if I use negation of whatever is announced, then how is that different from removing arrows? Is it different?
Look at this mode. Two states, not P and P. The agent cannot distinguish them. Previously, an announcement of P reduced the model to this, right? In the new semantics, we have to draw all arrows. Previously, that meant, well, still the same, but that means that you just keep this arrow, right? in the new model, an announcement of P get you to this. Which now can not only be executed if P is true, but also if P is false. But then after the announcement of P, even if P is false, then the agent believes that P is true. Yeah. Not at the end of the story. Now I can, in fact, distinguish two versions. It's like a story beyond that. Two versions of that new semantics. One version wherein, after all, you require as precondition for the execution that what being announced is true. That I call a truthful public announcement. And another that requires as precondition that what is being announced is false. That I call a lying public announcement. On that assumption, truthful public announcements can only be executed if P is actually true, the underlining, so to speak. If you end up here, that is indistinguishable from the one where this arrow is also removed. It doesn't matter, because it's pointing to, it's not moving away. But if the requirement is that the announced formula is false, that is the one that can only be executed from this point. And that is actually what's happening in the last line. Yeah. History, we don't have to see this. More complex dynamics. New topic. Back to public announcements as restricting the model to a submodel. It's also compatible with the other story, but let's stick to the reducing something story. There are actions that cannot be modeled as model restrictions. In other words, there are actions that cannot be modeled as truthful public announcements. And, well, if I say it like that, it's almost self-evident because there are actions that are not public. There are actions that are differently observed by the agents who are affected by new incoming information. An example in the setting of cards is the action of showing a card to another player. So here we have our model for the three cards again. N, Bill, Kath, and where N holds 0, Bill 1, and Kath 2. And now we want to model the action that N shows her card to Bill. And you can, well, you might say you can observe that is there any deal of cards where N cannot show her card to another player? No, that's always possible. Well, is there any deal of cards wherein she holds 0? Well, no, on condition that she's showing card 0. Is there any deal of cards wherein she cannot show card 0 to another player? Yes, all the deals where she doesn't hold card 0, right? Here it's useful to distinguish you might say, the description of the action independently from the card she actually holds from the one when you know what that card is. And that distinction is a bit similar to the distinction between, between an epistemic model that describes what agents know and do not know about each other, and being able to point at the actual state in that model. So actually showing card 0 is what really happens, given that what could have happened is that she showed the card she had, whatever it was, 0, 1, or 2. But the main thing there is that in the action of showing the card she has, whatever it would be, then no single card deal will be eliminated from consideration, so it's not a model restriction. So we have to find another, well, way to represent this information change. Apparently something is wrong now. No. This is what I want. Now, let's see if you can agree to what I want. If N is showing her card to Bill, well, Bill is going to learn that card. Bill was uncertain about the two cards, so that uncertainty would now be removed. You had a question?
No, only an observation. Now Cat knows that Bill knows all the cards.
Yes.
The only new observation which Cat has.
Yeah, excellent point. So here's when higher order knowledge comes into play. From this action of N showing her card to Bill, it's not merely the case that Bill now knows all cards, but it's also then the case that Kath knows that Kath knows that Bill now knows all cards. Yeah. And here we can verify this in the model, right? So this was the actual distribution of cards. Here, Bill was uncertain between 0, 1, 2 and 2, 1, 0. Bill was uncertain if N had 0 or 2. Well, so you expect this uncertainty to remove after this card showing action, and indeed it has disappeared. So what we changed is actually the accessibility relation, and what we did is that we refined it. Because reflexive arrows are still there, now all the states are singletons for Bill. But if N had card 1, and she were to show Bill her card, then the uncertainty would also have disappeared, so that resulted in this. And Kath, yeah, I'm probably going to say that. Kath was uncertain between these two. But it's, imagine that we remove this arrow, but do not remove this arrow. That would be strange, right? Because Kath is supposed to learn that whatever happened, Bill would now have learned what the card deal is, but of course Kath doesn't know what card Bill has. She only knows that whatever card he had, he would now have learned N's card. So we expect the link to disappear here, but also to disappear here. Well, similarly, even though N is showing her card to Bill, N doesn't know what card Bill has, right? So even for her, the only thing she has learned is that Bill now knows the card deal, whatever the card deal is. So N cannot distinguish these two deals, but she doesn't want only this to remove, but also that to remove. So we need to remove all the indistinguishability relations for Bill. Bill would now know the card deal, whatever the card deal is.
In fact, it's common knowledge.
And in fact, it's common knowledge, yes. Yeah. Well, there's a simple trick to do this, what I have just explained by example. And this trick is to have a representation of this action as something that is like a Kripke model, but not exactly, when I'm saying the word Kripke model, I tend to use epistemic model. This is for me the main thing. Maybe I should, I should not write this down. I'm calling it Kripke model because Kripke is the person who invented these models. Yeah. This is a relational structure, this is a relational structure. This is the one that represents knowledge and ignorance that the players have about each other. This is the one that represents knowledge and ignorance that players have about the actions that they perform. There are 3 actions to perform for N: showing card 0, showing card 1, or showing card 2. And you can talk your way through an argument that makes it justifiable that Kath, who cannot observe what card has been shown, should therefore in principle be unable to distinguish between all these 3 show actions. Well, in fact, depending on the actual card she has, she is able to make some distinction because she has card 2, so she knows it can't be 2. But, given that this should work from whatever perspective the players have on each other, N doesn't know that Kath is card 2, for example, we need to take all these alternatives into account. But one thing you can be sure of is that if N shows a card to Bill, N and Bill are aware of this. Anne and Bill are seeing that card at the same time. So for them, it's like a public announcement on the level of the two agents only. There is one difference between these representations, although it's both a relational structure here and there. Here, if I write, well, here in a state, you have to be explicit about what propositional variables are true and false in that state. This we call the valuation. Here, well, in an action, I wouldn't call it a state, but an action. Here, in a point in this relational structure, you have to be explicit about the precondition for execution of this action, which can be any formula in the logic. So it's not a valuation, but a precondition. Other than that, no difference. Then what you do is, well, you multiply. But for relational structures, this is a standard operation. You take the modal product of this and this structure, but 6 times 3 is 18, and there are only 6 things on the right-hand side, so it's not exactly a modal product, but it's a restricted modal product. Well, when do you take a pair of something here and there? If the action can be executed in that particular state. When can you execute the action show with card 0? Well, if n holds card 0, so only here and here, but not these 4. So this one matches with this and this, and similarly, showing card 1 can only happen if n has card 1, and showing card 2 can only happen if n has card 2, and that's the only 6 pairs of the restricted domain of the product. But other than that, things go, well, you might say, more standard again. Now, when would I say that two states are indistinguishable? Well, if they were indistinguishable here and if they were indistinguishable there. Or, in other words, if you're uncertain between two states and you're uncertain about whether one of two actions is being executed in these two states, then you will still be uncertain about their outcomes. Now, this is exactly what's the case for Cath. N is shown card 0. Cath is uncertain between n shown card 0 and card 1. But no, I'm being imprecise. Cath is uncertain between n having card 0 or card 1. But she is also uncertain between n showing card 0 or card 1. Well, we should put a C-link, indistinguishable link, between this pair and this pair. If there was a link between the first arguments of the pair, here, and if there was a link between the second arguments of the pair, which is the case here. Bill was uncertain between n having card 0 or card 2. In both these states, a show action can be executed. We end up with a pair for this cardinal where card 0 is shown, and for this cardinal where card 2 is shown. When should we put an indistinguishability arrow between these pairs? Well, if the states were indistinguishable and if the actions were indistinguishable. But the actions are not indistinguishable. Bill can see whether card 0 or card 2 is being shown. So between these, there's no B-link here. So there is no B-link here, because even though there is a B-link here, there is no B-link in this structure between these two actions. So this you compute for all, and then you're done. I can say this in much more detail by giving you this story, and I will skip this story. This essentially says what I've just said by example. And I think, given the time, it's better now to continue with some other topics I want to address before we run out of time for this lecture. Another thing I can say is, okay, how do we connect this up to a logic? In a way, it's all fairly simple. It becomes fairly simple if you explain it 10 times too, but maybe not if you see it for the first time. We had logic with public announcements. Now we're talking about more complex actions. Is there a way to unify one with the other? Yeah, public announcements are also these action models that I've just explained, but with just a unique action. It's a singleton action model. So the structure that you associate to a public announcement as an action is a singleton, where the singleton is observed, well, this is the unique action being observed by all agents, so it's a singleton with reflexive arrows for all agents. And the generalization of the logic of public announcement to the logic of action models is to replace the operator for public announcement in the logic by an operator for action models in the logic, which then can be any action model, including public announcement. This is going from here to here. And just as the precondition for, well, making a public announcement is that it's truthful, is that phi is true, the precondition for executing an action is that the action can be executed. So well, and we call this indeed a precondition. So that is also similar. Still, I'm doing a couple of tricks here and sleight of hand that I'm not explaining, because an action model is a semantic object, and all of a sudden I'm putting semantic objects in the logical language. You're not supposed to do that. Well, in a different setting, you can talk your way through seeing this, after all, as a syntactic object. Well, related to there's something called well, a different logic called PDL with actions, and you can also consider automata as actions. So an action model is like a small automaton that you add to the language, and another, you might say, short, fast explanation through this is if we can see this action model, such as the showing card action, right? The 3 points that are indistinguishable. It was an action model consisting of 3 points, and in all these points we had a precondition. Now, if you do not think of this as an object with preconditions, but as an object without preconditions, such as a relational frame, these preconditions are just fillers of the positions in this frame to do something. So this frame you can see as some kind of function that takes things of type formula as input, those are the preconditions. That can be followed by another formula, which we call the postcondition, and that outputs something again that is a formula. Okay, so that's a recipe to make a formula from a formula, so this we can put in a BNF. So then you see this, what we have introduced as a semantic object, instead as one of an innumerable set of labels that we can call frames, but that still sounds semantic, but it's just adding another parameter to the inductive definition of language. So there's a way to get around this. I see Ram looking doubtful. Yeah. Okay. Now that we have seen muddy children, let us do muddy children with cleaning. Sunil, you have seen this, right? Yeah. This is the one we have seen. Okay. Now, picture. A bucket of water enters the story. So after saying that at least one of you is muddy, father cleans and in public. Well, there's some further assumptions here, but let us not be too picky. So it's clean water. Yeah, so the result of throwing a bucket of water over N is that she is indeed clean, and that this is common knowledge, right? Yeah. So this was what we had. At least one of you is muddy. Will you step forward if you know whether you're muddy? Will you step forward if you know whether you're muddy? Blah, blah, blah. And we had the 3 children version where 2 of the 3 are muddy, and Bill. And we insert a new action. Father empties a bucket of water over N. What's going to happen? The rest remains the same. So what will happen? Well, yeah. I would say that N would step forward at least. She knows that she's clean, right? But there's a difference which makes life harder, because N stepping forward no longer has the same, well, meaning as it used to have. Because N stepping forward used to mean that she was seeing two clean children. And now it no longer means that. And in fact, it's a nice example of a trivial action. It was common knowledge that N was clean, so N stepping forward doesn't have any informative effect. Everybody knew that this was going to happen. Okay, so the question is, what else could happen that would make this interesting? No, if this question were repeated again, would now other people step forward? Not so clear, right? Let us put this through, well, other imaginary examples. Suppose that only Bill was muddy, and that N and Kath were clean. Now father throws a bucket of water over N. Bill finds this incredibly funny because he could see that N was already clean. Now father says, if you know whether you're muddy, please step forward. Who will step forward? Yeah, Bill and N, both, right? Yeah. And for Bill it's meaningful, but for N not. Okay, let me, in a way we've already achieved the end. Suppose that Bill and Kath are muddy and N is clean. What will happen? Father asks, if you know whether you're muddy, please step forward. No, N will step forward. But what will happen then? Yeah. Then Bill and Kath will step forward because they can still see that the other is muddy, right? So if only one of them had been muddy, they would have expected the other to step forward together with N. But it didn't happen, therefore they both step forward the second time. Okay, now N and Bill are muddy, as in here, and well, so Bill sees that N is muddy initially, so he's uncertain about his muddiness, right? So he will not step forward at the first request. Will he step forward at the second request? No. That would require a bit more explanation, but what happens is that we now get, to cut a long story short, we now get these transitions where the first announcement is as before, well, at least one of you is muddy. Then the making clean, well, for me, I thought of this version. For me, this was interesting because the making clean, well, it's not here as an assignment. It's an action that more than an action in the sense of artificial intelligence, where you shoot guns, physical action, right? Not information change, but actual change. So for me, this is a story that, well, for me demonstrates that if you combine information change with factual change or ontic change or whatever way you may call this, then you can get interesting and surprising interactions. So in modeling systems, it's therefore, well, maybe not interesting, but at least very relevant to pay careful attention to, well, how these two different sort of change affect each other. And well, given that this was the actual situation, then here N will step forward and here actually nothing will happen because, well, to cut the story short, for the muddy children problem to work, you need the induction to get started. You need a base step after which you can go forward Like, oh, then it must be at least one muddy child. Oh, then it must be at least two. Oh, then it must be at least three. If n is cleaned, you can't get the induction started again because it invalidates, you might say, the initial announcement that made it work. But only for groups wherein n was a member, but not for groups eliminating her. So for B and C, it still works. Well, only for muddy groups involving n as a member, not for muddy groups not involving n as a member. So father can repeat his request infinitely often and nothing further will happen. No full knowledge is realized. Yes?
If he would repeat his first announcement, it would work, right?
Yes. That would work, and I wouldn't even know how exactly it would work. I'd have to compute it carefully.
After cleaning n.
Yeah.
Right. Now Bill, he doesn't see anybody who's muddy, right?
Exactly. So Bill would learn that he's muddy. Yes. So Bill would now step forward. Yes. But I'm wondering how it would. Yeah. So that is correct. I'm wondering how it would address the situation in the other points here. Well, maybe after all it's possible. So if now he said at least one of you is muddied, only this removes.
Yeah, it reduces to just two.
Hmm?
It reduces to just Bill and Cal.
Yeah. He steps forward. Yeah, but but it removes the uncertainty for Keth too then. So at least the second time this request is made, then Keth would step forward. I think that's it. So first N, then Bill, then Keth. Yeah. Because from Bill stepping forward, Keth would learn that. Yeah. Oh, I could make this was still in PS tricks. I don't want to do this anymore. I should now use ticks or something, but I could make a more complex picture of this now. Yeah. Okay. So it's interesting to combine factual change with information change. The example I gave here combines it with public announcements. So instead of public announcement, you can have public assignments. And, well, throwing a bucket of water in the presence of everybody, that's really a public sort of action, right? But you also have private factual change. Well, you can do, so there's this 100 prisoners in a light bulb riddle where you switch a light bulb secretly when you are in an interrogation room and the other prisoners don't see you. So this interaction of knowledge and facts, knowledge change and factual change also occurs in the setting of non-public actions. And both these things can be made into, axiomatizable logics, and these changes actually turn out to be quite trivial. So this is, theoretically, it's not a big deal, but it's, in the sense that it doesn't affect the expressivity of the logics, but it allows you to model far more interesting multi-agent systems, so more interesting dynamics. And there's some other interesting things, such as it affects the complexity of both, well, at least I think of both model checking and satisfiability. So there are a number of other interesting aspects there. Yeah. Okay, that was one issue, and here we go on to the next one, belief revision. In view of the time, let me not do this, but talk you through the example, and this is an example. So it's the same setting. You can explain this entire branch of model logic by using a single propositional variable for everything, and then all the complexities are the modalities. So here again, P false or P true, right? Just like the one here on the blackboard. There was an equivalence class. Now I required a bit more of you. Instead of drawing a link between these two states to identify that they're in the same class, I boxed them. So this is just saying that they are indistinguishable. But there's a smaller box in the bigger box, and the smaller box means that this is considered more plausible than that. So we enrich the structures. The structures are not merely relational structures with binary relations for each agent that stand for indistinguishability, where the special case is where this is equivalence relations that represent knowledge. But we further require that in such an equivalence class there is internal structure. Well, this internal structure is a well pre-ordered, but you might say it's ordered. And this order we call plausibility or preference. And it means that the agent, well, only knows that P or not P is the case but can't choose, but the agent considers it more possible that P is the case. Now what happens if you are being fed the information from the outside that tells you, no, actually not P is more plausible? Well, then I just change my beliefs and I say, well, I can still not rule out either P or not P, but now from the alternatives P and not P, I find not P more plausible than P. And something else comes with this story. You know something if it's true in all the states that you consider possible. Okay, so here there's not that you know very much because you know P or not P. In this logic, well, there is equivalence relations and plausibility relations.
What are the other way?
Sorry?
Ordering that you have on the picture.
Yeah.
You have 0 greater than 1. I thought you said that 1 is more plausible.
Yes. It's you might say it's for historical reasons. People like to think of being more plausible as being at the bottom of some stack, the bottommost layer. Well, this other than historical reasons. So it's a well-founded thing where the thing that you consider most plausible, well, is indeed at the bottom. And if you see it as a bottom, then this is below that. But it means that one is, well, P is more plausible than not P. Or that the innermost layer is more plausible than the outermost layer. Now, how do you use this bottom of the stack? Well, things that are true at the bottom of the stack are things that you believe. So you know something if it's true anywhere, and you believe something if it's true in the most plausible states. So you believe P. If you go from here to here, then you believe not P. What does this sort of information change say? Well, if I believe P, and I receive new information that tells me that actually not P is to be believed, then on the assumption that I find this new incoming information more reliable than my actual beliefs, I would then be inclined to change my beliefs into the opposite. So from a disparate aspect, it's a merging of two forms where this one takes priority over that one. Okay. This priority thing becomes a nice other picture with that. This one. More complex example. So most things can be explained by single variable, but let's use two. P and Q. P first digit, Q second digit. P and Q can be false, P can be true, Q false, P and Q can be both true. The innermost square is what is most plausible, what is at the bottom. And then beyond that comes another, well, not square, but a squared polygon, and becomes then an outer square. So this represents that the agent believes the 1, 1. So the agent believes that P and Q are true. The agent, well, believes with a slightly lower degree of confidence all the things that are in these three states, which is actually that P or Q is true. And the agent knows, well, only that P and Q are relevant variables of which it wants to know the truth. So the agent doesn't know very much here. Now, given that the agent believes that P and Q are both true, the agent receives the information that P is false and wants to incorporate that new information. But preferably so in a way that this change is, minimal according to some measure of minimality. Let's bypass that. But the idea is that the new incoming information has now the primate over the old existing information. But, you might say, where it doesn't matter given the new information, you keep your old distinctions between more and less plausible. Here P is false, here P is true. If you receive the information that P is false and you want to do something with that information, those two things should not both become more plausible than those two things, those two states. But within this distinction, you still consider this more plausible than that. And within the within the P states, you still consider this more plausible than that. Well, so if you redraw the lines, then we now get this innermost, this second, this third, and that fourth. So here, as said here, before the agent believes P, because that's innermost here. After revision, the agent believes not P, because not P is true here. And other than that, we can observe that now the agent actually believes not P and Q. So the agent has kept its belief in Q. So this is the aspect of the minimality. If you first believe P and Q, and then you're presented with a not P, you might throw away the P, but keep the Q. This is what happens. So now the agent believes not P and Q, it's slightly less plausible, at least believes not P, etc. Time is progressing, I should finish, right? A nice logic can come out of that. I'll allow myself another 5 minutes. Yeah. One other thing you can do, maybe I shouldn't do this, so this was to be a warm-up for Jan Jing's part of the talk. Let me present the warm-up as a small 1-minute story in the 5 minutes that I have left. Executing an action is a tick of a clock. Well, it doesn't have to be, but suppose it's a tick of a clock. Well, there are logics for clock ticks, which are called temporal logics, logic of time. So executing a sequence of actions is, time progresses. Well, there are lots of modal operators for progressing time, like the F for there is something in the future such that, or G for every point in the future this and that. So there is a way to link the dynamic epistemic logic that I have been presenting here to temporal epistemic logic, where you do not have actions that are interpreted by model transformers, but temporal modalities. But wait a minute, temporal modalities are interpreted how? Well, because you have a model wherein you have an internal accessibility relation associated with these temporal modalities. But the dynamic epistemic modalities were not interpreted by internal steps in a model, but by transforming the model. So that means we have to devise something from transforming, that talks transforming a model into doing an internal step, in some other setting. Well, that other setting is a bigger model that contains all these model restrictions from some initial model. So instead of a model with a restriction and another restriction and another restriction, ignore the details, we then get a bigger model where the double arrows now have become single arrows. So then these model transformations are now internal steps in a bigger model. I think Jan Jing will tell more about this. But if you're talking about these temporal modalities, you can actually think of a sequence of announcements or a sequence of actions such that something happens in the future as well, a modality in itself that says diamond phi, well, if there is an announcement after which phi. Diamond phi if there is a model restriction after which phi. What is diamonds is like a temporal F modality, a future modality. And that's like talking about sequences of model restrictions that can take any shape. So, apart from translating dynamic epistemic logic into temporal epistemic logic, where at least you have that the dynamic epistemic actions become next point in time things in a temporal setting, we have another more general point of view where even the other temporal modalities have correspondence in a dynamic epistemic logic. I will not talk about that. And then there are many other things that you can do, on which I will not talk much, but maybe a bit. I've said a bit about things like complexity. Well, no, I didn't say anything at all about complexity, but I said a bit about succinctness, such that the public announcement logic is more succinct. So there are a lot of interesting things to say about that. I did say fairly little about applications. I mentioned here in the security protocols in my examples. Another, I think, promising area for examples is what is known in the area as gossip protocols, network protocols where information disseminates by peer-to-peer calls. So these are private to the sender and receiver of those calls, right? So we need these are not public information changes, but more of the private kind that I didn't describe in detail, and you need then to apply that sort of logic to describe those transitions. What I didn't do is proof theory. But fortunately, Olivier is here in the room, and anything you want to know about proof theory, well, at least a large interesting part of that is going to appear or has already appeared in a special issue of the Journal of Logic and Computation. So there are lots of things you can do with proof theory in dynamic epistemic logic too. That's this one. And then there's protocols on which Yanjing will talk. And oh yeah, and just to mention this, lots of further reading on any of these topics, like belief revision separate, or temporal epistemic logic separate, or just public announcement separate, or in a forthcoming handbook of epistemic logic, of which the all chapters will be downloadable open source, so you can just take this off from the web. Yeah. Okay, thank you very much. Yeah.
What about multi-agent system?
Sorry?
Multi-agent came from the last handbook of Expressivity.
Yeah.
Multi-agent system.
Yeah. So many examples of systems with multiple agents. Yes. Yeah. And yeah, another chapter on security protocols, for example. Yeah. Okay. Yeah.